All right, this video is going to talk about mutually exclusive events and addition rule for probability. So two events are mutually exclusive if they cannot occur at the same time, or the probability that A and B happen are 0. One way that we can show this in a Venn diagram is that they have two separate circles in your Venn diagram with nothing in common in the middle. There is an example that you can read through right here that shows you where A and B are not mutually exclusive because they share 4 and 5. However, C and A would be mutually exclusive because they don't share any of the outcomes. In the addition rule, what we are going to end up saying is the probability that A happens or B happens is that you can add A and B, but then you have to subtract out the intersection. Again, I'm going to show you this in a Venn diagram. If I have A and B that are not mutually exclusive, so they have an overlap, and you add the probability of A and the probability of B, then you've counted this intersection, this and piece, twice. So we correct that by subtracting it out. However, if A and B are mutually exclusive, then this probability is 0. And so you can just add these, and the probability of A or B happening just becomes adding those two, and you don't have to worry about any kind of overlap. Let's look at an example to make sure that we don't confuse mutually exclusive with independent. So if C and D are independent, then what that means is the probability of C given D has happened, which in this case it says is 75%, should be equal to just the probability that C happens. And notice that that is true. Therefore, yes, these two events are independent from each other. Are C and D mutually exclusive? Well, we would need to look at the and probability and notice that that is not equal to 0. Therefore, no, they are not mutually exclusive. So yes, independent, not mutually exclusive. If I wanted to try to figure out what the probability of D given C is, well, if they are independent, then that probability should just be the probability of D happening, which is 0.3. Another way that we can look at this, though, is the probability of D and C happening over the probability of C. When you plug in the numbers that are given and you do that division, you do find that it is 0.3, and so that's just another way that you can look at that probability. All right, let's continue and look at a distribution table here that includes some 4 very well-known baseball players and their hits over their careers. So if I wanted to find the probability, I choose a hit and it was made by Babe Ruth. Well, one way that I could do that is just take his total hits and divide by the total. If I want to find the probability that it was a double, again, I can just take the probability of, or the total of all the doubles over the total. If I want to find the probability that the hit was a double and that it was hit by Babe Ruth, well, that's only this intersection, if you will, of being both Babe Ruth and a double. So I'm going to say that that's only 506 out of the total. That's different than if I were to say like, hey, if I know I'm only looking at Babe Ruth's hits, so the probability of a double given it was Babe Ruth, well, now my totals are only out of the Babe Ruth totals. And so I'm going to look at his doubles out of his total because I was told in the problem that I'm only looking at Babe Ruth. One more example that I want us to look at that's not in here that I'm going to add is what's the probability of Babe Ruth or double? Now, because there is an intersection piece, then I'm going to take the probability to be all of Babe Ruth's hits plus all of the doubles. But when I do that, when I add these two totals together, I've counted 506 twice. So I'm going to subtract out the and or the intersection in order to find that probability.